Hello and welcome to the Sleepy Science channel. I'm glad you found your way here tonight. Maybe it's been a long day. Maybe the world felt a little too noisy, a little too fast, and you needed somewhere calm to land. Whatever brought you here, you're welcome. Just settle in. Close your eyes if you'd like. Let your breathing slow and let the evening carry you somewhere ancient and deep. Tonight, we're going underground, far beneath the surface of the Earth, into the restless, molten interior of our planet, where forces of unimaginable power have shaped the history of life itself. We're going to talk about supervolcanoes and mass extinctions, about the moments when the Earth turned against its own inhabitants, not out of malice, but out of physics, out of heat and pressure and chemistry and time. These are stories of devastation, yes, but also of resilience, of life pushed to the edge and finding a way back, of a planet that destroys and creates in equal measure, endlessly, patiently, across billions of years. Now, the word supervolcano might sound alarming, and the phrase mass extinction even more so. But I think you'll find, as we walk through these stories slowly and gently, that there is something strangely calming about them. Not because the events themselves were peaceful, they were anything but because they happened so long ago and on such vast timescales that they take on a quality of deep geological patience. The Earth breathes slowly. Its heartbeat is measured in millions of years. And tonight, we'll listen to that heartbeat together. Before we begin, if these quiet explorations help you relax, drift off to sleep, or simply bring a bit of calm to the end of your evening, consider tapping the like button and subscribing. It helps others find their way here too, one sleepy soul at a time. And if you'd like, let me know in the comments where in the world you're listening from, or what topic you'd like to explore next. Now, let's begin to understand supervolcanoes. We need to first understand what's happening beneath our feet. The ground feels solid. It feels permanent. When you walk across a field or stand on a mountain, the Earth seems utterly still, utterly reliable. But that solidity is an illusion. Beneath the thin crust we live on, a layer just a few tens of kilometers thick, the Earth is in motion. It is hot, it is fluid, and it is restless. The interior of the Earth is divided into layers. At the very center lies the inner core, a solid ball of iron and nickel about 1,200 kilometers in radius, compressed to unimaginable density by the weight of everything above it. The temperature at the center of the Earth is roughly the same as the surface of the Sun, about 5,400 degrees Celsius. Surrounding the inner core is the outer core, a layer of liquid iron and nickel about 2,200 kilometers thick. This liquid metal, churning and convecting in slow, massive currents, generates the Earth's magnetic field, the invisible shield that protects us from the solar wind and cosmic radiation. Above the outer core lies the mantle, a thick layer of rock that extends from about 35 kilometers below the surface down to about 2,900 kilometers. The mantle is not liquid in the everyday sense. It's solid rock, but over geological timescales, millions of years, it flows, it convects. Heat from the core rises through the mantle in vast, slow currents, like water heating in a pot, carrying energy from the deep interior toward the surface. These convection currents are the engine that drives plate tectonics, the slow movement of the Earth's crustal plates across the surface. And at the very top, the crust, thin, brittle, fractured into a dozen major plates and many smaller ones, floating on the mantle like crackers on a bowl of thick soup. The plates move slowly, just a few centimeters per year, roughly the speed at which your fingernails grow. But over millions of years, those centimeters add up, continents drift, oceans open and close, mountain ranges rise and erode. The geography of the Earth is constantly changing, constantly being rewritten by the slow, patient forces beneath. Volcanoes are one of the most dramatic expressions of this internal heat. They occur where molten rock, called magma, finds a pathway from the interior to the surface. This can happen at the boundaries between tectonic plates, where plates pull apart, or where one plate slides beneath another, or at hotspots, places where an unusually intense plume of heat rises from deep in the mantle, melting the rock above it and pushing magma toward the surface. Most volcanoes are relatively modest affairs. A cone-shaped mountain, a crater at the top, periodic eruptions of lava, ash, and gas. They can be destructive, certainly. Mount Vesuvius buried Pompeii in 79 AD. Mount Helens exploded in 1980, flattening forests and sending ash across the continent. Mount Pinatubo erupted in 1991 and cooled the entire planet by half a degree for a year. These are significant events. They reshape landscapes, disrupt weather, and sometimes kill thousands of people. But they are not supervolcanoes. A supervolcano is something else entirely. Something on a scale so far beyond ordinary volcanism that it almost belongs to a different category of natural phenomenon. If an ordinary volcanic eruption is a firecracker, a supervolcanic eruption is a nuclear bomb. The difference is not just in degree, it's in kind. The term supervolcano is informal. Volcanologists prefer to talk about eruptions rated on the Volcanic Explosivity Index, or VEI, a scale that runs from 0 to 8. Each step on the scale represents roughly a 10-fold increase in the volume of material ejected. A VEI-1 eruption might produce a few tens of thousands of cubic meters of ash and lava. A VEI-5 eruption, like Mount St. Helens, produces about a cubic kilometer. A VEI-7 eruption, like the 1815 eruption of Mount Tambora in Indonesia, produces tens to hundreds of cubic kilometers. A VEI-8 eruption, a supervolcanic eruption, produces more than 1,000 cubic kilometers of material. 1,000 cubic kilometers. That's enough ash and rock and pumice to bury an entire country under meters of debris. Enough to fill a lake larger than some seas. Enough to change the chemistry of the atmosphere, block sunlight across the entire planet, and alter the course of evolution itself. These eruptions are rare, vanishingly rare by human standards. The last VEI-8 eruption occurred about 26,500 years ago at what is now Lake Taupo in New Zealand. Before that, the most recent was the eruption of the Toba supervolcano on the island of Sumatra, about 74,000 years ago. And before that, you have to go back millions of years to find comparable events. They happen, on average, perhaps once every 100,000 years or so, though the interval is highly variable. On the timescale of a human life, they are essentially non-existent. On the timescale of geology, they are routine. Let's look more closely at what a supervolcanic eruption actually involves, because the details are extraordinary. A supervolcano doesn't look like a regular volcano. It doesn't have the classic cone shape that we associate with mountains like Fuji or Vesuvius. Instead, a supervolcano is often marked by a caldera, a vast sunken depression in the Earth's surface, formed when a previous eruption emptied the magma chamber beneath and the ground above collapsed into the void. Calderas can be enormous. The Yellowstone caldera, the most famous supervolcano in the world, is roughly 72 kilometers long and 55 kilometers wide. It's so large that early explorers didn't recognize it as a volcanic feature at all. They thought they were just looking at a valley. Beneath the caldera lies the magma chamber, or rather the magma reservoir, because recent research has shown that the system beneath Yellowstone is not a single chamber, but a complex network of partially molten rock extending deep into the mantle. The upper part of the reservoir, the part closest to the surface, is estimated to contain about 10,000 cubic kilometers of material, of which perhaps 5 to 15% is actually molten. The rest is hot but solid rock, a crystalline mush that slowly circulates and evolves over thousands of years. Magma reservoirs build up over very long periods of time. Magma rises from the mantle, accumulates in the crust, and slowly differentiates, the heavier minerals sinking, the lighter ones rising, the dissolved gases concentrating in the upper portions. Over tens of thousands or hundreds of thousands of years, the reservoir grows, the pressure builds, and the chemistry of the magma changes. Silica content increases. Dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide, become more concentrated. The magma becomes thicker, stickier, more viscous, and more explosive. Because here's the key fact about volcanic explosions. It's not the lava that makes them dangerous, it's the gas. When magma is deep underground, the enormous pressure keeps the dissolved gases trapped in the liquid, much like carbon dioxide is dissolved in a sealed bottle of sparkling water. But as the magma rises toward the surface, the pressure drops and the gases begin to come out of solution. They form bubbles. The bubbles expand. And if the magma is thick and viscous, as it is in silica-rich supervolcanic systems, the bubbles can't escape gently. They build up pressure. And when that pressure exceeds the strength of the rock above, the result is an explosion, not a gentle outpouring of lava like you might see in Hawaii, but a cataclysmic detonation that shatters the overlying rock, hurls cubic kilometers of material into the atmosphere, and generates pyroclastic flows, superheated avalanches of gas, ash, and rock, fragments that race across the landscape at hundreds of kilometers per hour, incinerating everything in their path. A supervolcanic eruption begins with a sound that defies imagination. Or rather, it begins with a pressure wave, because the sound itself would be beyond the range of human hearing, a deep infrasonic pulse that would be felt more than heard, rattling through the Earth's crust and radiating outward through the atmosphere. The ground above the magma chamber, already bulging and cracking from the pressure beneath, fractures along ring faults, enormous circular cracks that outline the caldera. And through these cracks, the magma erupts. The eruption column, a pillar of superheated gas and ash, rises into the atmosphere at speeds exceeding the speed of sound. It can reach heights of 40 to 50 kilometers, punching through the troposphere and into the stratosphere, carrying with it billions of tons of ash, pumice, and sulfur compounds. In the first hours and days, the column may collapse repeatedly, generating pyroclastic flows that radiate outward from the caldera in every direction, burying the surrounding landscape under meters of hot ash and pumice. The scale of destruction in the immediate vicinity of a supervolcanic eruption is total. Within a radius of perhaps 100 kilometers, everything is obliterated. Forests are flattened and incinerated. Rivers are dammed by debris. The landscape is resurfaced, buried under a thick blanket of volcanic material that can remain hot for years, even decades. Nothing survives, nothing grows. The land is sterilized. But the truly significant effects of a supervolcanic eruption are not local, they are global. Because the material injected into the stratosphere doesn't just fall back to Earth immediately. The heavier particles, the ash and pumice, settle out within weeks or months, blanketing the surrounding region and affecting areas hundreds or even thousands of kilometers downwind. But the lightest particles, and especially the sulfur dioxide gas, can remain in the stratosphere for years, spread around the entire globe by high-altitude winds. Sulfur dioxide, when it reaches the stratosphere, reacts with water vapor to form sulfuric acid aerosols, tiny droplets of sulfuric acid suspended in the air. These aerosols are extraordinarily effective at reflecting sunlight. They act like a planetary sunscreen, bouncing incoming solar radiation back into space before it can reach the surface. The result is cooling, significant, sustained, global cooling. After a large eruption, even one much smaller than a supervolcanic event, the effect on global temperatures can be dramatic. The 1991 eruption of Mount Pinatubo, a VI6 event, injected about 20 million tons of sulfur dioxide into the stratosphere. Global temperatures dropped by about 0.5 degrees Celsius for the following year. Sunsets around the world turned vivid shades of red and orange, painted by the sulfuric acid haze high in the atmosphere. Crop yields in some regions declined. Weather patterns were disrupted. Now scale that up by a factor of 100 or 1,000. A supervolcanic eruption could inject hundreds or even thousands of times more sulfur dioxide into the stratosphere than Pinatubo did. The resulting cooling could be severe. Estimates suggest that a Yellowstone-scale eruption could lower global temperatures by 5 to 15 degrees Celsius for several years, perhaps longer. In the worst case, it could trigger what's sometimes called a volcanic winter, a prolonged period of cold and darkness that devastates agriculture, disrupts ecosystems, and challenges the survival of species around the world. The ashfall from a supervolcanic eruption would also be catastrophic over a wide area. Models of a potential Yellowstone eruption suggest that much of the western United States could be buried under centimeters to meters of ash. Cities hundreds of kilometers away would be blanketed. Airports would close. Water supplies would be contaminated. Power grids would fail as ash short-circuits transformers. Agriculture across the Great Plains, one of the world's most productive farming regions, would be devastated for years. And the fine ash particles, sharp-edged and abrasive, would pose severe respiratory hazards to humans and animals over a vast area. But let's step back from the human perspective for a moment and consider the deeper geological picture. Supervolcanic eruptions are not anomalies. They are part of the Earth's normal behavior. They have been happening for billions of years since the planet was young, and they will continue to happen for as long as the Earth has a hot interior. They are as natural as rain, as ordinary as erosion. They are simply part of how the Earth works, and they have, on several occasions, played a direct role in the most dramatic events in the history of life. Mass extinctions, moments when a significant fraction of all species on Earth disappeared in a geologically brief span of time. Let's talk about those now. The history of life on Earth is about 3.8 billion years long. For most of that time, life was microbial, single-celled organisms living in the oceans, slowly diversifying, slowly evolving, slowly changing the chemistry of the atmosphere and the oceans. The first multicellular organisms appeared around 600 million years ago. The first animals with hard shells and skeletons appeared around 540 million years ago in an event called the Cambrian explosion, a burst of evolutionary creativity that produced most of the major animal body plans we see today. And from that point on, the fossil record becomes rich enough for us to track the rise and fall of species, families, and entire ecosystems with reasonable precision. What the fossil record shows is a history of life that is not smooth and steady, but punctuated, interrupted. There are long periods of relative stability, when the diversity of life slowly increases, when new species evolve and old ones persist, when ecosystems grow more complex and more interconnected. And then, suddenly, there are crashes. Moments when the diversity of life plummets, when ecosystems collapse, when species vanish by the thousands or millions in what amounts to a geological instant. These crashes are the mass extinctions, and the fossil record reveals 5 major ones in the last 540 million years, events so severe that they are sometimes called the Big Five. Each one wiped out a significant percentage of all species on Earth. Each one fundamentally reshaped the trajectory of evolution, and each one was followed, eventually, by a recovery, a new burst of diversification as the survivors evolved to fill the empty ecological niches left behind. The Big Five mass extinctions are the Ordovician-Silurian extinction, about 444 million years ago, the Late Devonian extinction, about 372 million years ago, the Permian-Triassic extinction, about 252 million years ago, the Triassic-Jurassic extinction, about 201 million years ago, and the Cretaceous-Paleogene extinction, about 66 million years ago. Each one has its own story, its own causes, its own victims, and its own aftermath. And while not all of them are directly linked to supervolcanism, several of them are. The role of volcanic activity in shaping the history of life is one of the great themes of Earth science, and it's a story that has only become clear in the last few decades. Let's begin with the most famous mass extinction of all, the one that killed the dinosaurs, the Cretaceous-Paleogene extinction, often abbreviated as the KPG extinction, K for Kreide, the German word for Cretaceous, and PG for Paleogene, occurred approximately 66 million years ago. It wiped out about 76% of all species on Earth, including all non-avian dinosaurs, the marine reptiles like mosasaurs and plesiosaurs, the flying reptiles called pterosaurs, and the ammonites, a group of shelled marine creatures that had been abundant for hundreds of millions of years. The extinction was sudden. Geologically speaking, it happened in the span of perhaps a few thousand years, possibly less, a blink of an eye in geological time. For decades, the cause of the KPG extinction was debated. Many hypotheses were proposed: climate change, sea level fluctuations, disease, competition with mammals. But in 1980, a father and son team of scientists, Luis and Walter Alvarez, along with their colleagues Frank Asaro and Helen Michel, published a groundbreaking paper proposing a radical new idea. They had discovered an unusual layer of clay at the boundary between Cretaceous and Paleogene rocks, a thin band rich in the element iridium. Iridium is rare on Earth's surface, but relatively common in asteroids and meteorites. The Alvarez team proposed that the iridium had been delivered by a massive asteroid impact, an event so violent that it had triggered a global catastrophe, blotting out the sun and devastating the biosphere. The hypothesis was controversial at first. Many paleontologists were skeptical, but over the following years, evidence accumulated. The iridium anomaly was found at KPG boundary sites around the world, suggesting a global event. Shocked quartz grains, minerals that can only be formed under the extreme pressures of an impact, were found in the same layer. Tiny glass spherules called tektites, formed when molten rock is blasted into the atmosphere and solidifies as it falls, were found in profusion. And in 1991, researchers identified the impact crater itself. It was buried beneath the Yucatan Peninsula of Mexico, centered near the town of Chicxulub. The Chicxulub crater is approximately 180 kilometers in diameter and 20 kilometers deep. It was formed by an asteroid estimated at about 10 to 15 kilometers across, roughly the size of a mountain, traveling at about 20 kilometers per second when it struck the Earth. The energy released by the Chicxulub impact was almost incomprehensible. Estimates range from about 100 trillion tons of TNT to perhaps 10 billion times the energy of the atomic bomb dropped on Hiroshima. The impact vaporized both the asteroid and the vast volume of the Earth's crust, sending a plume of superheated rock vapor and debris into the upper atmosphere. The shockwave would have generated earthquakes of magnitude 11 or greater, far beyond anything in recorded history. Tsunamis hundreds of meters high would have swept across the Gulf of Mexico and radiated outward through the world's oceans. Wildfires, ignited by the rain of incandescent debris falling back through the atmosphere, may have swept across entire continents. But the most lethal effect was probably the dust and soot. The impact injected an enormous quantity of fine particulate matter into the stratosphere, creating a global shroud that blocked sunlight for months, possibly years. Photosynthesis ceased, temperatures plummeted, the food chain collapsed from the bottom up. Plants died, herbivores starved, carnivores followed. In the oceans, plankton populations crashed, undermining the entire marine food web. It was a global winter, triggered not by ice but by dust, a darkness that descended on the entire planet and lasted long enough to reshape the tree of life. But here's where the story gets more complicated and where supervolcanoes enter the picture. Because the KPG extinction didn't just coincide with the Chicxulub impact, it also coincided with one of the largest volcanic events in Earth's history, the Deccan Traps. The Deccan Traps are a massive igneous province in what is now Western India. An igneous province is a region where enormous volumes of lava have been erupted over a geologically short period of time, covering vast areas of the Earth's surface in thick layers of basalt. The Deccan Traps cover an area of roughly 500,000 square kilometers, about the size of France, and in some places the lava flows are more than 2 kilometers thick. The total volume of lava erupted is estimated at over 1 million cubic kilometers. This is not a single volcanic eruption. It's a sustained episode of volcanism that lasted for about 1 million years, centered around the time of the KPG boundary. Now, the eruptions that created the Deccan Traps were not supervolcanic eruptions in the sense of a single cataclysmic explosion. They were flood basalt eruptions, events where vast quantities of lava well up through cracks in the Earth's crust and flow across the landscape in enormous sheets. Individual eruption episodes within the Deccan volcanic sequence may have lasted for decades or centuries, each one releasing staggering quantities of lava, carbon dioxide, and sulfur dioxide into the atmosphere. The cumulative effect of the Deccan Traps volcanism on the global environment would have been severe. The carbon dioxide released would have driven long-term global warming. The sulfur dioxide would have caused short-term cooling and acid rain. The combination of warming and cooling, of acidification and chemical disruption, would have stressed ecosystems worldwide, weakening species and reducing biodiversity even before the asteroid arrived. So what actually killed the dinosaurs? The asteroid, the volcanoes, or both? This question has been one of the most fiercely debated in paleontology for the past 2 decades. Some researchers argue that the Chicxulub impact was the sole cause of the extinction, that its effects were so devastating that nothing else was needed. Others argue that the Deccan Traps volcanism had already pushed the biosphere to the brink, and the asteroid merely delivered the final blow. And still others suggest that it was the combination of both, a 1-2 punch that no ecosystem could withstand. The current scientific consensus, if there is one, leans toward the impact as the primary trigger for the sudden extinction event at the KPG boundary. The timing is too precise, the evidence too overwhelming for the asteroid to be dismissed. But the Deccan Traps volcanism almost certainly played a supporting role, stressing ecosystems and reducing their resilience in the hundreds of thousands of years leading up to the impact. And in the aftermath, the continued volcanism may have slowed the recovery, making it harder for surviving species to rebound. It's a fascinating example of how multiple catastrophic processes can interact, each one compounding the effects of the others. The Earth, during the last days of the Cretaceous, was being assaulted from above and below simultaneously, and life, caught between an asteroid and a volcano, didn't stand a chance. At least, not most of it. But some species survived. Mammals, small and adaptable, endured. Birds, the descendants of theropod dinosaurs, made it through. Crocodilians, turtles, and snakes survived in freshwater environments. Insects persisted, as they always do. And in the oceans, some fish, some invertebrates, some deep-sea organisms weathered the storm. The survivors inherited a devastated world, but a world full of empty niches, vacant ecological real estate, waiting to be claimed. And over the next few million years, they diversified explosively, filling the gaps left by the vanished dinosaurs. Mammals grew larger, birds radiated into thousands of species. Flowering plants, already diversifying before the extinction, became the dominant form of vegetation. The modern world, the world of grasslands and forests, and coral reefs and whales and primates, and eventually us, was born in the aftermath of the KPG extinction. Now, let's go back further in time to the greatest mass extinction of all, the one that makes the KPG extinction look modest, the Permian-Triassic extinction, often called the Great Dying. The Permian-Triassic extinction occurred approximately 252 million years ago at the boundary between the Permian and Triassic periods. It was the most severe biological crisis in the entire history of complex life. Estimates vary, but the most commonly cited figures suggest that about 90 to 96% of all marine species and about 70% of all terrestrial vertebrate species went extinct. Some groups were hit even harder. Trilobites, those iconic marine arthropods that had been abundant for hundreds of millions of years, vanished entirely. Most corals disappeared. Most brachiopods, bryozoans, and crinoids were wiped out. On land, the dominant reptiles, the therapsids and the parasaurs, were decimated. Insects suffered their only known mass extinction. Forests disappeared in many regions, replaced by fungal blooms as dead wood rotted across the landscape. The scale of the Great Dying is difficult to comprehend. Imagine walking through a forest and removing 9 out of every 10 trees. Imagine diving into a coral reef and taking away 95 out of every 100 fish. Imagine a world where almost everything alive simply ceases to exist, replaced by emptiness, by silence, by the slow decay of what was left behind. That is what the Permian-Triassic extinction looked like. And the cause? Volcanoes, specifically the Siberian Traps. The Siberian Traps are the largest known continental flood basalt province on Earth. They cover an area of roughly 2 million square kilometers in what is now Siberia, Russia, and in places the lava flows are several kilometers thick. The total volume of erupted material is estimated at between 1 and 4 million cubic kilometers. The eruptions began slightly before the Permian-Triassic boundary and continued for about 1 million years, though the most intense phase may have lasted only a few 100,000 years, perhaps even less. The Siberian Traps eruptions were different from ordinary volcanism in important ways. The magma rose through rocks that were rich in organic carbon, coal deposits, limestone, and evaporites, sedimentary rocks formed from the evaporation of ancient seas. As the magma intruded into these rocks, it heated them, baking them, and releasing enormous quantities of gas, carbon dioxide from the limestone, methane, and other hydrocarbons from the coal, halogenated compounds from the evaporites, sulfur dioxide from the magma itself. The result was a toxic cocktail of gases injected into the atmosphere on a scale never seen before or since. The environmental consequences unfolded in waves. The sulfur dioxide caused short-term cooling and acid rain, damaging plant life and acidifying surface waters. The carbon dioxide caused long-term warming, a greenhouse effect that raised global temperatures by perhaps 8 to 10 degrees Celsius over several 100,000 years. The oceans warmed, and as they warmed, they lost dissolved oxygen, because warm water holds less gas than cold water. Vast stretches of the ocean became anoxic, dead zones where nothing that breathed oxygen could survive. The acid rain and ocean acidification destroyed the shells of marine organisms, dissolving the calcium carbonate that corals, mollusks, and foraminifera depended on. The methane released from the baked coal deposits may have made things even worse. Methane is a powerful greenhouse gas, far more effective at trapping heat than carbon dioxide, though it doesn't last as long in the atmosphere. And as the oceans warmed, there may have been an additional feedback. The warming may have destabilized methane hydrates, ice-like deposits of methane trapped in sediments on the ocean floor. If these hydrates released their methane, it would have amplified the warming further, creating a runaway greenhouse effect that pushed temperatures even higher. The ozone layer may also have been damaged. Some of the gases released by the Siberian Traps, particularly the halogenated compounds from the evaporites, are known to destroy ozone. If the ozone layer was significantly thinned, it would have allowed increased ultraviolet radiation to reach the Earth's surface, damaging plants, plankton, and other organisms, adding another layer of stress to an already collapsing biosphere. The evidence for this catastrophic chain of events comes from many sources. Chemical analyses of rocks from the Permian-Triassic boundary show spikes in carbon isotope ratios, indicating a massive injection of light carbon into the atmosphere, consistent with the release of volcanic carbon dioxide and the burning or baking of organic-rich sediments. Oxygen isotope ratios indicate rapid warming. Boron isotopes in marine carbonates suggest a drop in ocean pH consistent with acidification, and the timing of the Siberian Traps eruptions, as determined by radiometric dating, matches the timing of the extinction with remarkable precision. The Great Dying was not a sudden event like the asteroid impact that ended the Cretaceous. It was a prolonged crisis, a slow-motion catastrophe that unfolded over hundreds of thousands of years. Some researchers have identified multiple pulses of extinction within the Permian-Triassic interval, suggesting that the environmental stresses intensified in waves, each one pushing more species over the edge. The biosphere was weakened by the initial volcanic emissions, then hammered again and again as the eruptions continued, and the secondary effects, warming, anoxia, acidification, cascaded through the system. The recovery from the Great Dying was extraordinarily slow. For millions of years after the extinction, ecosystems remained impoverished. The fossil record shows a period sometimes called the Dead Zone, a long interval of low diversity during the early Triassic, when only a handful of species dominated in any given environment. Fungal spores are abundant in the rock record of this interval, suggesting that dead organic matter was everywhere, decaying across the landscape. Coral reefs, those engines of marine biodiversity, didn't fully recover for about 10 million years. It took the biosphere something like 5 to 10 million years to reach pre-extinction levels of diversity. But recover it did, and the world that emerged from the Great Dying was profoundly different from the one that preceded it. The dominant groups of the Permian, the large synapsid reptiles, the ancient corals, the trilobites, were gone. In their place, new groups arose. The archosaurs, a lineage that would eventually give rise to dinosaurs, crocodilians, and birds, became dominant on land. New types of corals evolved to build reefs. New families of fish, mollusks, and marine reptiles filled the emptied oceans. The Mesozoic era, the age of dinosaurs, was born from the ashes of the Permian. Let's continue our journey through time and look at the other major mass extinctions and the role that volcanic and other geological processes played in each. The Ordovician Silurian extinction, about 444 million years ago, was the first of the Big Five. It occurred in two pulses, separated by about a million years. The first pulse coincided with a rapid glaciation, a sudden cooling event that locked up enormous volumes of water in ice sheets, lowering sea levels and exposing the continental shelves where most marine life lived. The second pulse occurred as the ice melted and sea levels rose again, flooding the shelves with anoxic, oxygen-poor water that poisoned the returning marine fauna. The cause of this glaciation is not entirely clear. Some researchers have proposed that it was driven by a drawdown of atmospheric carbon dioxide, perhaps caused by increased weathering of silicate rocks exposed by tectonic uplift. Others have suggested a role for volcanic activity, or even for the evolutionary success of early land plants, whose roots would have accelerated the chemical weathering of rocks, pulling carbon dioxide from the atmosphere and cooling the climate. The link to volcanism is less direct here than in the Permian or Cretaceous extinctions, but the broader point remains. The Earth's internal processes, the movement of plates, the rise of mountains, the eruption of volcanoes set the stage for the extinction by altering the chemistry of the atmosphere and the configuration of the continents. The late Devonian extinction, about 372 million years ago, was actually a series of extinction pulses spread over roughly 20 million years, with the most severe events concentrated in two intervals, known as the Kellwasser and Hangenberg events. Marine life was devastated, with reef ecosystems collapsing entirely. The Great Devonian reefs, built by rugose and tabulate corals and stromatoporoids, were destroyed and would not be replaced for millions of years. The causes of the late Devonian extinction are still debated, There is evidence for ocean anoxia, for global cooling, for changes in sea level, and for increased nutrient runoff from the newly evolving land plants, whose roots were breaking down rocks and releasing nutrients into rivers and oceans, potentially triggering algal blooms that consumed oxygen and created dead zones. Some researchers have also proposed a link to large igneous province volcanism, specifically the Vilu traps in Siberia, though the evidence is less conclusive than for the Permian or Cretaceous events. The Triassic-Jurassic extinction, about 201 million years ago, was the fourth of the Big Five and is perhaps the most directly linked to volcanic activity after the Permian-Triassic event. It occurred at the boundary between the Triassic and Jurassic periods and wiped out about 76% of all species, including many of the large amphibians and reptiles that had dominated the Triassic. Among the casualties were most of the crurotarsans, the crocodile-line archosaurs that had been the dominant land predators. Their extinction cleared the way for the dinosaur-line archosaurs, the true dinosaurs, to become the dominant terrestrial animals, a position they would hold for the next 135 million years. The cause of the Triassic-Jurassic extinction is strongly linked to the Central Atlantic Magmatic Province, or CAMP, one of the largest igneous provinces in Earth's history. CAMP eruptions occurred as the supercontinent Pangaea began to break apart, tearing along a rift that would eventually become the Atlantic Ocean. The eruptions covered an area of perhaps 11 million square kilometers with basalt lava, and they released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. The environmental effects were similar to those of the Siberian traps during the Great Dying, rapid warming, ocean acidification, anoxia, and ecological collapse, though perhaps somewhat less severe. The pattern is striking. 3 of the Big Five mass extinctions, the Permian-Triassic, the Triassic-Jurassic, and arguably the Cretaceous-Paleogene, are directly associated with large igneous province volcanism, and in each case, the mechanism is similar. Enormous volumes of lava erupt over geologically short periods of time. The gases released alter the chemistry of the atmosphere. The climate shifts, sometimes cooling, sometimes warming, often both in succession. The oceans acidify, oxygen levels drop, and the biosphere, stressed beyond its capacity to adapt, collapses. This is not a coincidence. It reflects a deep truth about how the Earth works. The same internal heat that drives plate tectonics, that creates new ocean floor and pushes continents around the globe, also periodically erupts in catastrophic volcanic episodes that can reshape the entire surface of the planet and the life upon it. The Earth is a dynamic system, and like all dynamic systems, it has modes of behavior that are stable and modes that are not. Most of the time, the system operates in a relatively stable mode. Volcanoes erupt at plate boundaries. Earthquakes shake the crust. Erosion and sedimentation reshape the landscape. Life evolves slowly, adapting to gradual changes. But occasionally, the system tips into a different mode. A mantle plume reaches the surface. A continent sits over a hot spot. An enormous volume of magma accumulates and finds its way to the surface, and the result is a large igneous province, a flood basalt eruption, a global environmental crisis, a mass extinction. Let's pause here for a moment and let these ideas settle. The Earth beneath you is alive, not in the biological sense, but in the geological sense. It is hot, it is moving, it is churning and convecting and releasing heat and creating new crust and destroying old crust in a continuous cycle that has been running for 4.5 billion years. And that cycle, that restless geological engine, has been the backdrop for the entire history of life. It has created the conditions that allowed life to evolve, and it has on occasion nearly destroyed it. But life is resilient. That's the other side of the story. After every mass extinction, no matter how severe, life recovered. It took time, sometimes millions of years, sometimes tens of millions, but it always came back. New species evolved, New ecosystems assembled. New forms of life arose to fill the niches left empty by the vanished. And in many cases, the new world was more diverse, more complex, and more productive than the one that preceded it. The Cambrian explosion followed the severe glaciations of the Cryogenian, when the Earth may have been almost entirely covered in ice, a scenario known as Snowball Earth. The diversification of fish and the colonization of land followed the Ordovician extinction. The rise of the dinosaurs followed the Triassic-Jurassic extinction. The rise of mammals and birds followed the KPG extinction. Each catastrophe, however devastating, opened the door to new possibilities, new evolutionary experiments, new ways of being alive. This doesn't mean that mass extinctions are good in any moral or human sense. They are not. They are immense tragedies of biodiversity, wiping out lineages that had endured for millions of years, eliminating forms of life that will never exist again. But from the perspective of deep geological time, they are also creative forces. They prune the tree of life, sometimes savagely, but in doing so, they create space for new branches to grow. The biosphere after an extinction is like a forest after a fire, devastated in the short term, but fertile, full of light and nutrients and open ground, ready for something new. Let's now look more closely at some of the individual supervolcanic eruptions that have occurred in relatively recent geological time, events that we can study in more detail because the evidence is better preserved. The eruption of Toba on the island of Sumatra in Indonesia about 74,000 years ago is the most recent supervolcanic eruption of VEI 8 magnitude. It was an enormous event, ejecting an estimated 2,800 cubic kilometers of material, making it one of the largest eruptions in the last few million years. The eruption created the caldera that is now filled by Lake Toba, the largest volcanic lake in the world, about 100 kilometers long and 30 kilometers wide. The Toba eruption has been the subject of intense scientific debate, particularly regarding its effects on the global climate and on the human species. Some researchers have proposed that the eruption triggered a volcanic winter lasting 6 to 10 years, with global temperatures dropping by as much as 3 to 5 degrees Celsius for several years, and possibly much more in some regions. This cooling, combined with the destruction of vegetation by ashfall, may have caused a severe ecological crisis, reducing the populations of many species and creating a bottleneck in the human population. The genetic evidence is intriguing. Analyses of human DNA have revealed that our species went through a severe population bottleneck sometime around 70,000 to 100,000 years ago, a period when the total human population may have dropped to as few as a few thousand or even a few hundred breeding individuals. Some researchers have proposed that the Toba eruption was the cause of this bottleneck, that the volcanic winter it triggered nearly drove our species to extinction. This is the Toba catastrophe theory, and it remains controversial. Critics point out that the genetic bottleneck is not precisely dated and may not coincide exactly with the Toba eruption. They also note that archaeological evidence from some regions shows continuous human occupation through the Toba event, suggesting that the effects may not have been as universally catastrophic as the theory proposes. And recent climate modeling suggests that the cooling effect of Toba, while significant, may have been less severe than earlier estimates indicated, perhaps 1 to 2 degrees Celsius of global cooling, rather than 3 to 5. Regardless of whether Toba nearly wiped out humanity, it certainly had a profound impact on the global environment. Ash from the eruption has been found in sediment cores from the Indian Ocean, the South China Sea, and across the Indian subcontinent. In some parts of India, the ash layer is several meters thick, even at distances of thousands of kilometers from the eruption site. The sulfuric acid aerosols injected into the stratosphere would have affected the climate for years, and the local devastation in Southeast Asia would have been immense, destroying forests and displacing or killing animal populations across a vast area. Let's also consider Yellowstone, the most famous supervolcano on Earth. Yellowstone sits atop a mantle plume, a column of abnormally hot rock rising from deep in the Earth's interior. As the North American plate has moved westward over this plume over the past 16 million years, the plume has created a chain of volcanic centers, each one marked by caldera-forming eruptions, stretching from southwestern Idaho to northwestern Wyoming. Yellowstone has produced 3 major caldera-forming eruptions in the past 2.1 million years. The first, about 2.1 million years ago, created the Huckleberry Ridge caldera and ejected about 2,500 cubic kilometers of material. The second, about 1.3 million years ago, created the Mesa Falls caldera and ejected about 280 cubic kilometers. And the third, about 640,000 years ago, created the current Yellowstone caldera and ejected about 1,000 cubic kilometers. Each of these eruptions was a catastrophic event, blanketing much of North America in ash and altering the global climate. The interval between these eruptions is roughly 600,000 to 800,000 years, which has led to some popular speculation that Yellowstone is overdue for another eruption. This is a misconception. Volcanic systems don't operate on precise schedules, and the intervals between eruptions are too variable and the sample size too small to make meaningful predictions. The United States Geological Survey, which monitors Yellowstone continuously, currently assesses the probability of a caldera-forming eruption in any given year as approximately 1 in 730,000. In other words, while such an eruption is certainly possible, it's not particularly likely in any given millennium, let alone any given year. Still, the monitoring continues. Yellowstone is one of the most closely watched volcanic systems on Earth. An extensive network of seismometers, GPS stations, satellite instruments, and ground-based sensors tracks the park's geological activity in real time. Earthquakes are recorded, many of them tiny, barely perceptible. The constant chatter of a geologically active system. Ground deformation is measured with millimeter precision. Gas emissions are sampled and analyzed. Hot spring temperatures are monitored. Any significant change in any of these parameters would trigger increased attention, and if warranted, a public alert. The current state of Yellowstone is one of quiet activity. The ground surface rises and falls by a few centimeters over periods of years, driven by the movement of fluids and gases in the subsurface. Earthquake swarms occur periodically, clusters of small earthquakes that reflect the shifting and cracking of rock deep underground. Hot springs and geysers, including the famous Old Faithful, continue to erupt on their regular schedules, a surface expression of the heat that flows relentlessly from below. There is nothing in the current data to suggest that an eruption, let alone a supereruption, is imminent. But let's imagine, just for a moment, what such an eruption would look like if it did occur. Not as an exercise in fear, but as an exploration of the power that lies beneath the Earth's surface. The warning signs would probably come weeks or months in advance. Increased seismicity, faster ground uplift, changes in gas emissions. The USGS would issue alerts, evacuations would begin, and the world would watch with a mixture of fascination and dread. And then at some point, the magma would breach the surface. The eruption would begin along the ring faults that define the caldera. Fissures would open in the earth, and magma, propelled by the pressure of dissolved gases, would fountain upward, sending columns of ash and gas tens of kilometers into the atmosphere. Pyroclastic flows, dense currents of superheated gas and rock fragments, would race outward from the vents at hundreds of kilometers per hour, devastating everything within a radius of perhaps 80 to 100 kilometers. Within hours, the landscape around the caldera would be unrecognizable, buried under meters of hot pyroclastic material. The ash column would spread across the continent, carried by prevailing winds. Within days, much of the western and central United States would be covered in ash, thicker near the eruption site and thinning with distance. Even cities 1,000 kilometers away might receive several centimeters of ashfall, enough to collapse roofs, contaminate water supplies, ground aircraft, and cripple infrastructure. The ash would be a fine, gritty powder, rich in glass shards that damage lungs and abrade machinery. Cleaning it up would take years. The global effects would unfold over weeks, months, and years. The sulfur dioxide injected into the stratosphere would form sulfuric acid aerosols, reflecting sunlight and cooling the planet. Global temperatures might drop by several degrees Celsius. Growing seasons would shorten. Crop failures would ripple through the world's food supply. Famine in many regions would be a real possibility. The effects on global trade, transportation, and geopolitics would be profound and unpredictable. But the world would survive. Humanity would survive. We are, as a species, remarkably adaptable. We have technology, knowledge, and organizational capacity that no previous species has possessed. A Yellowstone supereruption would be a catastrophe of the first order, but it would not be an existential threat. The human race would endure, as it has endured ice ages, volcanic winters, famines, plagues, and countless other trials. Battered, diminished perhaps, but alive, and eventually the ash would settle. The aerosols would dissipate. The climate would recover. New vegetation would colonize the devastated landscape, slowly at first, then with increasing vigor. The caldera itself would fill with water, forming a new lake, a peaceful surface hiding the violence beneath, and life, as it always does, would go on. Let's turn now from supervolcanoes to another type of geological upheaval that has played a role in mass extinctions: oceanic anoxic events. An oceanic anoxic event, or OAE, is an interval during which large portions of the ocean become depleted of dissolved oxygen. Without oxygen, most marine life cannot survive. Fish die. Invertebrates perish. The only organisms that thrive are anaerobic bacteria, microbes that can live without oxygen, often producing hydrogen sulfide as a byproduct, a gas that is toxic to most other forms of life. The oceans, in effect, become poisonous. Oceanic anoxic events have occurred multiple times in Earth's history, and they are often associated with periods of global warming, high carbon dioxide levels, and volcanic activity. The mechanism is straightforward. When the atmosphere warms, the oceans warm as well. Warm water holds less dissolved oxygen than cold water. At the same time, increased temperatures can accelerate the decomposition of organic matter in the water, a process that consumes oxygen. And if nutrient runoff from the land increases, perhaps because of enhanced weathering driven by acid rain or volcanic emissions, it can trigger algal blooms. The algae grow, die, sink to the bottom, and decompose, consuming even more oxygen. The result is a vicious cycle. Warming leads to oxygen depletion. Oxygen depletion kills marine life. Dead marine life sinks and decomposes, consuming more oxygen, and the ocean, from the bottom up, becomes a dead zone. The most severe oceanic anoxic events in the geological record are associated with mass extinctions. The Permian Triassic extinction, which we discussed earlier, was accompanied by widespread ocean anoxia, as evidenced by the deposition of black, organic-rich shales in marine sediments from around the world. The late Devonian extinction also shows signs of ocean anoxia, and several smaller extinction events, the so-called minor mass extinctions that pepper the geological record between the Big Five, are also associated with anoxic episodes. One of the most intriguing aspects of ocean anoxia is the production of hydrogen sulfide. When ocean water becomes anoxic, sulfate-reducing bacteria take over, consuming sulfate ions in the water and producing hydrogen sulfide, H2S, as a waste product. Hydrogen sulfide is toxic to most organisms, even in small concentrations. In large quantities, it can kill marine life, damage the ozone layer, and even poison terrestrial ecosystems. Some researchers have proposed that during the worst episodes of ocean anoxia, hydrogen sulfide may have accumulated in the deep ocean, eventually erupting to the surface in massive toxic plumes, killing marine and coastal life and damaging the atmosphere. This scenario, sometimes called a Canfield Ocean after the geochemist who first proposed it, is based on evidence from the chemistry of ancient sediments. Certain minerals and biomarkers found in rocks from the Permian-Triassic boundary are consistent with a sulfide-rich, oxygen-poor ocean, and the presence of specific organic molecules produced by photosynthetic sulfur bacteria, organisms that thrive in waters where hydrogen sulfide reaches the sunlit surface, has been detected in rocks from several mass extinction intervals. The picture that emerges is one of an ocean turned inside out. Instead of the oxygen-rich, life-sustaining waters we know today, the Permian-Triassic Ocean may have been a vast, stratified, poisonous body, with a thin, oxygenated layer at the very top and a deep, anoxic, hydrogen sulfide-rich layer beneath. The boundary between these layers may have migrated upward during the worst phases of the extinction, reaching the surface in some regions and releasing toxic gas into the atmosphere. The sky may have turned green, tinted by the sulfur compounds in the air. The oceans may have smelled of rotten eggs, and the combination of heat, poison, and suffocation may have been too much for most forms of life to endure. Let's take a breath. That's a lot of death and destruction, and while it's all deep in the past, it can be heavy to contemplate. So let's lighten the mood just slightly by considering something remarkable. The fact that we're here at all. Every one of us is a descendant of survivors. Our ancestors, whoever and whatever they were, made it through every mass extinction, every volcanic winter, every ice age, every oceanic dead zone, every cosmic impact. They survived the Great Dying, when 90% of marine species perished. They survived the asteroid that killed the dinosaurs. They survived Toba. If the bottleneck theory is correct, when our species may have been reduced to a few thousand individuals huddled in a handful of refugia, we are the children of survivors. And that's not just a nice thought, it's a biological reality. The very genes in our cells carry the marks of those ancient crises. The metabolic pathways that keep us alive were forged in the fires of deep time. The immune systems that protect us were shaped by millions of years of microbial warfare. The resilience we carry as individuals and as a species is a gift from ancestors who endured conditions that would have killed most other lineages. Life, it seems, is harder to extinguish than you might think. The biosphere has been knocked down again and again, and each time it has gotten back up. Not the same as before, never the same, but alive, changed, adapted, and often more diverse than ever. Let's continue our exploration with some of the less well-known but equally fascinating volcanic events in Earth's history. About 260 million years ago, slightly before the Great Dying, another large igneous province erupted in what is now southern China. The Imatian Traps, as they're known, covered an area of perhaps 250,000 square kilometers with basalt lava. This eruption is associated with the Capitanian extinction, sometimes called the End Guadalupian extinction, a significant but less severe biotic crisis that preceded the Permian-Triassic event by about 8 million years. During the Capitanian extinction, many marine species disappeared, including a significant number of fusulinid foraminifera and brachiopods. The Imatian eruptions, like those of the Siberian Traps later, would have released large quantities of carbon dioxide and sulfur dioxide, disrupting the climate and the chemistry of the oceans. The Capitanian extinction is sometimes overlooked because it's so close in time to the Great Dying, which overshadows everything. But it may have been an important precursor, weakening ecosystems and reducing biodiversity before the main event. It's a reminder that mass extinctions don't always come as single events. They can come in clusters, like punches in a boxing match, each one weakening the biosphere's ability to absorb the next. About 183 million years ago, in the early Jurassic, the Karoo large igneous province, erupted across what are now South Africa and Antarctica. The torsion oceanic anoxic event, one of the most severe in the Mesozoic, occurred at roughly the same time. Ocean temperatures rose, oxygen levels in the deep ocean dropped, many marine species went extinct. The link between the volcanism and the anoxia is still being studied, but the coincidence is suggestive, and chemical evidence from the rock record supports a causal connection. About 120 million years ago, in the early Cretaceous, the Ontong-Java Plateau, one of the largest volcanic features on Earth, erupted on the floor of the Pacific Ocean. This submarine volcanic province covers an area roughly the size of Alaska and represents one of the most voluminous eruptions in the last 200 million years. The environmental effects of submarine volcanism are different from those of continental flood basalts. The lava enters the water rather than the atmosphere, so the direct atmospheric effects may be less pronounced. But the carbon dioxide released can still alter ocean chemistry, and the heat can affect deep ocean circulation patterns. The Ontong-Java eruptions are associated with OAE-1A, one of several Cretaceous oceanic anoxic events that disrupted marine ecosystems. These events, scattered across hundreds of millions of years of geological history, reveal a recurring pattern. Large volcanic episodes disrupt the climate and ocean chemistry. The disruptions cascade through ecosystems, causing extinctions, and the survivors evolve into new forms, filling the vacated niches and reshaping the biosphere. The pattern is not perfectly regular. The volcanic episodes are not evenly spaced. The extinctions vary in severity, but the general dynamic is the same. The Earth's internal heat, expressed through volcanism, periodically reshuffles the deck of life, dealing new hands and opening new games. Let's now consider what we know about the deep mechanisms that produce these volcanic outbursts. Because the more we understand about why they happen, the better we can assess the risks they pose and the role they've played in shaping the world we live in. The key concept is the mantle plume. A mantle plume is a column of abnormally hot rock that rises from the deep mantle, possibly from as far down as the core mantle boundary, 2,900 kilometers below the surface. The plume rises because it's hotter and therefore less dense than the surrounding mantle. As it rises, it partially melts, generating enormous volumes of magma. When the plume reaches the base of the lithosphere, the rigid outer shell of the Earth that includes the crust and upper mantle, it spreads outward, and the magma can erupt at the surface, creating a large igneous province. Mantle plumes are the leading explanation for both continental flood basalts, like the Siberian and Deccan traps, and oceanic plateaus, like the Ontong-Java Plateau. They are also responsible for volcanic hotspots, long-lived centers of volcanic activity that remain more or less stationary while the tectonic plates move over them. Hawaii is the best-known example. The Hawaiian Islands are the surface expression of a mantle plume that has been active for at least 80 million years. As the Pacific Plate moves northwestward over the plume, new islands are created, each one forming above the plume and then carried away, leaving a chain of progressively older volcanic islands and seamounts stretching across the Pacific. Yellowstone is another hot spot, though it's located on a continental plate rather than an oceanic one. The plume beneath Yellowstone has been active for about 16 million years, creating a chain of volcanic centers across Idaho and into Wyoming as the North American plate moved southwestward over the plume. The formation of a large igneous province is one of the most dramatic events in the Earth's geological repertoire. It requires an unusually large and energetic mantle plume, one capable of producing millions of cubic kilometers of magma over a relatively short period. The plume may be triggered by instabilities at the core mantle boundary, where the temperature contrast between the liquid iron core and the solid silicate mantle is enormous. Blobs of hot material may detach from this boundary layer and rise through the mantle over millions of years, finally reaching the surface and unleashing their energy in a vast volcanic episode. The timing and location of mantle plumes appear to be somewhat random, in the sense that they're driven by complex dynamics deep in the Earth's interior that are not yet fully understood or predictable. We can map the current locations of hotspots and plumes using seismic tomography, a technique that uses earthquake waves to image the interior of the Earth, much like a medical CT scan uses X-rays to image the body. These images have revealed several large structures in the deep mantle that may be the roots of active plumes, including one beneath Yellowstone and one beneath Hawaii. But predicting when and where the next large igneous province will form remains beyond our current capabilities. Let's also consider the role of plate tectonics in setting the stage for mass extinctions, even when volcanism is not directly involved. The configuration of the continents has a profound effect on global climate, ocean circulation, and the distribution of habitats. When the continents are scattered, as they are today, ocean currents can circulate relatively freely, distributing heat from the tropics to the poles and moderating the global climate. But when the continents cluster together, forming a supercontinent, the circulation is disrupted. The interior of the supercontinent becomes extremely continental in climate, with hot summers, cold winters, and limited rainfall. Ocean circulation is altered, sometimes producing large areas of stagnant, oxygen-poor water. And the concentration of land at particular latitudes can affect the planet's albedo, its reflectivity, influencing how much solar energy is absorbed and how much is reflected back into space. The Permian-Triassic extinction occurred when all the world's major landmasses were assembled into the supercontinent Pangaea. The vast interior of Pangaea was a desert, inhospitable to most forms of life. The oceans were dominated by a single vast body of water, Panthalassa, with a large embayment called the Tethys Sea between the northern and southern portions of the supercontinent. This configuration may have made the ocean's circulation more sluggish, more prone to stagnation and anoxia, and more vulnerable to the environmental perturbations caused by the Siberian traps. Volcanism. The breakup of Pangaea, which began in the Triassic and continued through the Jurassic and Cretaceous, was itself driven by mantle plumes and rifting. The Central Atlantic magmatic province, which erupted at the Triassic-Jurassic boundary, was associated with the initial rifting of Pangaea. The Deccan traps, which erupted at the Cretaceous-Paleogene boundary, were associated with the separation of India from Madagascar as it drifted northward toward its eventual collision with Asia. In each case, the volcanic activity was not a random event. It was a consequence of the deep geological processes that drive plate tectonics. The same forces that move continents also produce the volcanic events that can devastate life. This interconnection between plate tectonics, volcanism, climate, ocean chemistry, and the biosphere is one of the great themes of Earth science. The Earth is a system, a complex, dynamic, interconnected system in which changes in one component can cascade through others in ways that are often surprising and sometimes catastrophic. The mass extinctions are the most dramatic manifestations of this interconnection, moments when the normally slow and stable processes of geological change are amplified or disrupted, pushing the system past tipping points and into new, sometimes radically different states. Let's now shift our perspective and consider what these events can tell us about the present and the future. Because while supervolcanic eruptions and mass extinctions are rare events, they are not impossibilities. They have happened before, and they will happen again. The question is not if, but when. As we discussed, The Yellowstone supervolcano is currently being monitored with extraordinary care, but Yellowstone is not the only supervolcano on Earth. There are several other volcanic systems that have produced supervolcanic eruptions in the geological past and may be capable of doing so again. The Taupo volcanic zone in New Zealand produced the most recent VI8 eruption about 26,500 years ago. The zone remains highly active, with frequent smaller eruptions and ongoing geothermal activity. The Toba caldera in Sumatra, site of the massive eruption 74,000 years ago, is also still geologically active, with a resurgent dome, an island within the caldera that has been pushed upward by magma pressure that continues to grow. The Campi Flegrei caldera near Naples, Italy, is another supervolcanic system that has attracted considerable scientific attention. Campi Flegrei, which means burning fields in Italian, is a large caldera about 13 kilometers in diameter, partially submerged in the Bay of Naples. It has produced two major caldera-forming eruptions, the Campanian ignimbrite about 40,000 years ago, and the Neapolitan yellow tuff about 15,000 years ago. The Campanian ignimbrite eruption ejected about 200 to 300 cubic kilometers of material, making it one of the largest eruptions in Europe in the past 200,000 years. The eruption may have contributed to the decline of Neanderthal populations in Europe, though this remains debated. Campi Flegrei has been in a state of unrest since the 1950s, with periodic episodes of ground uplift, earthquake swarms, and increased gas emissions. In the 1980s, the ground surface rose by about 1.8 meters over a period of 2 years, triggering the evacuation of tens of thousands of people from the town of Pozzuoli. The uplift has since partially reversed, but activity continues, and the system is closely monitored by Italian volcanologists. The Long Valley caldera in eastern California is another major volcanic center. It was formed about 760,000 years ago by the eruption of the Bishop Tuff, which ejected about 600 cubic kilometers of material and blanketed much of the western United States in ash. The caldera is still geologically active, with ongoing seismicity, ground deformation, and emissions of carbon dioxide. A resurgent dome within the caldera has risen about 80 centimeters since the 1980s. These systems remind us that the Earth's internal heat is not a thing of the past. It continues to flow, to build, to accumulate. And while the probability of a supervolcanic eruption in any given year is extremely low, the cumulative probability over long periods of time is significant. Over the next 100,000 years, there is a meaningful chance that one or more of these systems will produce a major eruption. Not necessarily a V8 super eruption, but possibly a VEI7 or even VA8 event that would have global consequences. The challenge of preparing for such an event is immense. We can monitor volcanic systems, detect warning signs, and evacuate nearby populations. But the global effects of a supervolcanic eruption, the climate cooling, the ashfall, the crop failures, would be felt far beyond the immediate vicinity. Preparing for those effects requires a different kind of planning, one that involves food storage, agricultural adaptation, international cooperation, and the development of resilient infrastructure. These are challenges that humanity has only recently begun to think about seriously. Let's also consider a broader perspective on mass extinctions and what they teach us about the fragility and resilience of the biosphere. One of the most striking findings of recent paleontological research is that mass extinctions are not just rare, catastrophic events. They are formative events. They don't just destroy, they create. They reshape the trajectory of evolution, opening new avenues of diversification that would not have been available if the old ecosystems had persisted. The KPG extinction that killed the non-avian dinosaurs was the event that allowed mammals to diversify and eventually give rise to primates and eventually to us. Without that asteroid, without the Deccan traps, The mammals might have remained small, marginal, nocturnal creatures, living in the shadow of the dinosaurs for millions of years more. The world of grasslands and grazing herds and great apes and tool-using hominids might never have existed. Similarly, the Great Dying at the end of the Permian was the event that cleared the stage for the rise of the archosaurs, the group that includes dinosaurs, crocodilians, and birds. The therapsids, the mammal-like reptiles that had dominated the Permian, were devastated by the extinction. Their ecological niche was taken over by the archosaurs, which diversified rapidly in the early and middle Triassic. And the archosaurs, in turn, gave rise to the dinosaurs, which dominated the planet for the next 186 million years. This pattern, extinction followed by radiation, death followed by rebirth, is one of the most fundamental rhythms of life on Earth. It has repeated at least 5 times in the last 540 million years, and probably many more times in the deeper past before the fossil record becomes too sparse to read clearly. And each time, the biosphere that emerges from the extinction is different from the one that preceded it. Not necessarily better or worse, but different, changed, renewed. There's a lesson in that, I think. A lesson about the relationship between destruction and creation, between loss and renewal. The natural world is not a stable, static system. It is a dynamic, evolving, constantly changing tapestry, woven from the threads of birth and death, growth and decay, catastrophe and recovery. And the most transformative events in the history of life have often been the most destructive ones. This doesn't mean that destruction is good or that suffering has a purpose. It means that the story of life is resilient, that it continues even through the worst that the Earth or the cosmos can throw at it, and that the future, whatever it holds, will be shaped not only by the crises that come, but by the creativity of life in responding to them. Let's take a quiet moment here. Let the weight of deep time settle over you like a blanket. Millions of years, hundreds of millions, billions. The Earth has been here for 4.5 billion years, spinning and churning and reshaping itself, hosting life for nearly as long. And in all that time, through all those upheavals, life has persisted, changed form 1,000,000 times, survived ice and fire and poison and impact, but persisted. You are part of that persistence. Your breath, your heartbeat, your thoughts, your sleep, all of it is part of the longest story ever told. The story of life on Earth, a story written in rock and bone and DNA. A story that stretches back to the first self-replicating molecules in the primordial ocean and forward to a future we can only imagine. Let's continue with some more details about the mechanics of volcanism and its effects on climate, slowly and gently, as the evening deepens. One of the most important factors in determining the climatic impact of a volcanic eruption is the height to which the eruption column reaches. For volcanic gases to have a sustained effect on global climate, they need to reach the stratosphere, the layer of the atmosphere that begins at about 10 to 15 kilometers above the surface, depending on latitude and season. Material injected into the troposphere, the lower atmosphere where weather occurs, is quickly washed out by rain and snow. But material that reaches the stratosphere can remain suspended for months or years because there is no rain in the stratosphere. The sulfuric acid aerosols formed from volcanic sulfur dioxide can circle the globe in weeks and persist for 2 to 3 years before slowly settling out. The cooling effect of these aerosols is well documented. After the eruption of Mount Pinatubo in 1991, satellites measured a decrease in the amount of solar energy reaching the Earth's surface of about 2 to 3 watts per square meter. This doesn't sound like much, but it's equivalent to reducing the sun's total output by a fraction of a percent, and it was enough to cool the entire planet by 0.5 degrees Celsius. After the eruption of Mount Tambora in 1815, the cooling was more severe. The year 1816 became known as the year without a summer. In New England, there were frosts in June. In Europe, crop failures led to famine and social unrest. The skies were strange, hazy and discolored, and the sunsets were spectacular. Mary Shelley, spending a gloomy summer by Lake Geneva, wrote Frankenstein, inspired in part by the eerie sunless weather. A supervolcanic eruption would produce cooling on a much larger scale. Models suggest that a Yellowstone-scale eruption could reduce global temperatures by 5 to 10 degrees Celsius for several years, with the most severe cooling in the first year or two. To put that in perspective, the difference in global average temperature between the present day and the peak of the last ice age, about 20,000 years ago, was roughly 5 to 6 degrees Celsius. A supervolcanic winter could temporarily produce ice age-like conditions, though the cooling would be short-lived compared to a true ice age, which is driven by orbital and atmospheric changes that persist for tens of thousands of years. The ashfall from a supervolcanic eruption would also have significant effects. Volcanic ash is not like the soft, fluffy ash from a wood fire. It's composed of tiny fragments of glass and rock, sharp-edged and abrasive. When it falls on vegetation, it can strip leaves and damage crops. When it enters water supplies, it can contaminate them with dissolved minerals and heavy metals. When it's inhaled, it can damage lungs and cause silicosis, a chronic respiratory condition. And when it accumulates on roofs and structures, even a few centimeters of ash can add significant weight, leading to collapses. The distribution of ashfall depends on wind patterns at the time of the eruption. For a Yellowstone eruption, the prevailing winds would carry the ash primarily eastward across the Great Plains, the Midwest, and potentially as far as the East Coast. The thickest deposits, centimeters to meters, would be within a few hundred kilometers of the caldera. But detectable ashfall could cover much of the continent, and fine particles could remain suspended in the atmosphere for weeks, affecting air quality and visibility over a wide area. Beyond the immediate climatic and environmental effects, a supervolcanic eruption would have profound social and economic consequences. Modern civilization depends on complex, interconnected systems of food production, transportation, communication, and trade. A disruption as severe as a supervolcanic eruption would stress all of these systems simultaneously. Agriculture would be the most immediately affected. The combination of cold temperatures, reduced sunlight, and ashfall would devastate crops across vast areas. Even regions far from the eruption site would be affected by the global cooling and the disruption of trade networks. Food prices would spike. Famine would threaten vulnerable populations, and the cascading effects on economies, governments, and social stability would be difficult to predict and potentially severe. But humanity has faced severe challenges before and has found ways to adapt. The key to surviving a supervolcanic eruption, if one were to occur, would be preparation, coordination, and resilience. Stockpiling food, diversifying agricultural systems, developing cold-resistant crop varieties, strengthening international cooperation, and building redundancy into critical infrastructure would all contribute to our ability to weather the storm. And unlike the organisms that endured the mass extinctions of the past, we have something they did not: foresight, the ability to anticipate threats, to plan, to prepare, and to choose how we respond. Let's also briefly consider the relationship between volcanic activity and the origin of life itself. Because while volcanoes are often associated with destruction, they may also have played a crucial role in creating the conditions that allowed life to emerge in the first place. The early Earth, about 4 billion years ago, was a far more volcanically active place than it is today. The interior was hotter, the crust was thinner, and volcanic eruptions were more frequent and more intense. The atmosphere was composed primarily of volcanic gases: carbon dioxide, nitrogen, water vapor, and smaller amounts of methane, ammonia, and sulfur compounds. There was no free oxygen. The oceans were warm, possibly hot, and rich in dissolved minerals from volcanic vents. It was in this environment, harsh and inhospitable by modern standards, that the first self-replicating molecules may have formed. Some researchers have proposed that deep-sea hydrothermal vents, volcanic features on the ocean floor where superheated, mineral-rich water erupts from the Earth's interior, may have been the cradle of life. These vents provide a sustained source of chemical energy, a supply of raw materials, and a protected environment where complex organic chemistry could occur. The gradients of temperature, pH, and chemistry around the vents create conditions that are favorable for the kinds of reactions that might lead to the formation of amino acids, nucleotides, and eventually self-replicating molecules. Other researchers have proposed that life may have originated in volcanic hot springs on land, in pools of warm, mineral-rich water fed by volcanic activity. These pools would have undergone cycles of wetting and drying, concentrating organic molecules and promoting the kinds of chemical reactions that are thought to be important for the origin of life. Charles Darwin himself speculated about a warm little pond as the birthplace of life, and recent research has lent support to this idea. Whether life began in the deep sea or on land, in a hydrothermal vent or a volcanic pool, the role of volcanism was central. The heat, the minerals, the gases, the chemical gradients, all were products of the Earth's internal processes. Without volcanism, the early Earth would have been a very different place, and life, if it arose at all, might have followed a very different path. Volcanic activity also played a key role in maintaining the conditions that allowed life to persist and evolve over the following billions of years. The carbon cycle, the process by which carbon is exchanged between the atmosphere, the oceans, the biosphere, and the Earth's interior, depends critically on volcanism. Carbon dioxide is released into the atmosphere by volcanic eruptions and is removed by the chemical weathering of silicate rocks, a process that converts atmospheric CO2 into dissolved bicarbonate, which is eventually deposited as carbonate sediment on the ocean floor. Over millions of years, this sediment is carried into the Earth's interior by subduction, where it is heated, releasing the carbon dioxide again through volcanic emissions. This cycle, which operates on timescales of millions of years, acts as a thermostat, regulating the Earth's temperature and keeping it within the range that is compatible with liquid water and life. Without this volcanic thermostat, the Earth's climate would be far less stable. It might have frozen permanently during periods of low solar output, the so-called faint young sun problem, or it might have overheated during periods of high carbon dioxide. Instead, the volcanic carbon cycle has kept the Earth in a habitable state for most of its history, a remarkable feat of planetary self-regulation. So volcanoes are not just agents of destruction, they are also agents of creation. They built the atmosphere, they helped create the oceans, they may have sparked the origin of life, and they continue to regulate the global climate, keeping the Earth in the narrow range of conditions that allows the biosphere to thrive. They are, in a very real sense, the heartbeat of the planet. Sometimes the heartbeat is gentle and steady, and sometimes it pounds. Let's wind down the evening with a few more thoughts, gently as the night deepens. One of the things I find most comforting about the story of supervolcanoes and mass extinctions is the sheer resilience of life. Through all the catastrophes, through all the volcanic winters and oceanic dead zones and asteroid impacts, life has never been completely extinguished. It's been knocked down. It's been reduced to a fraction of its former diversity. But it has always recovered, always bounced back, always found a way. This resilience is not an accident. It's a property of the way life is organized. Biodiversity, the variety of species and ecosystems, is itself a form of insurance. When one species fails, another may succeed. When one ecosystem collapses, another may persist. The more diverse the biosphere, the more resilient it is. And over the long run, diversity tends to increase because evolution is an engine of innovation, constantly producing new forms, new strategies, new ways of making a living. The history of life on Earth is not a story of inevitable progress. It's a story of experimentation, of trial and error on a planetary scale. And the mass extinctions, for all their tragedy, are part of that process. They are the resets, the moments when the experiment is cleared and new variables are introduced. The results are unpredictable. The outcomes are often surprising. But the experiment itself, the grand experiment of life on Earth, continues, and we are part of that experiment. The most recent participants in a story that stretches back nearly 4 billion years. Our species is young, about 300,000 years old by current estimates. Our civilization is younger still. Our science, our technology, our understanding of the planet we live on are all products of the last few centuries. In the grand sweep of geological time, we are newcomers, barely arrived, still learning the landscape, but we bring something new to the story: awareness, understanding, the ability to read the rock record and decode the history of the Earth, the ability to monitor volcanoes and predict, at least approximately, when they might erupt, the ability to plan, to prepare, to mitigate. We may not be able to prevent a supervolcanic eruption. The forces involved are far too vast for any human technology to control. But we can understand them, we can watch for the signs, and we can build a civilization that is resilient enough to withstand the shocks that our restless planet will inevitably deliver. That's a hopeful thought to end the evening on. Not that the dangers don't exist, they do, but that we are not helpless. We are the first species in the history of the Earth that can look at the geological record, understand what it means, and take action to protect ourselves. That's a remarkable thing. A new chapter in the story of life on a volcanic planet. Let your mind drift now. Let the images of ancient seas and erupting volcanoes fade into the background. Let the timescales, the millions and billions of years, become soft and distant, like mountains on a far horizon. You don't need to hold on to any of it. The Earth will keep its stories safe, locked in layers of rock, waiting patiently for anyone who cares to read them. Think of the ground beneath you, if you like. The quiet, solid ground. It feels so stable, so permanent, and in human terms it is. The Earth beneath your home has been there for millions of years and will be there for millions more. The forces that shake and reshape the planet operate on timescales so long that they are invisible to us. In the span of a single life, the Earth barely changes. The mountains stand, the rivers flow, the seasons turn, and the ground holds firm. But deep beneath your feet, the mantle convects, the plates shift, magma rises and cools and rises again. The Earth is alive with heat, with motion, with the slow, patient energy of 4.5 billion years of cooling. And that energy, that restless geological engine, is the source of everything we see on the surface. The mountains, the oceans, the continents, the volcanoes, the hot springs, the geysers, the fertile soils that feed us. All of it comes from below. All of it is a gift from the Earth's interior. And the life that covers the surface, the forests and grasslands, and coral reefs, and cities and farms and gardens, all of it is sustained by the same processes. The volcanic gases that built the atmosphere, the minerals weathered from volcanic rocks that feed the soils, the heat that drives the water cycle, the plate tectonics that create new coastlines and mountain ranges and habitat diversity. Without the Earth's internal heat, the surface would be a dead, frozen, airless world like the moon. It's the fire below that makes the life above possible. So perhaps, instead of fearing the Earth's volcanic heart, we can appreciate it, not uncritically, not without awareness of the risks, but with gratitude for the role it has played in creating the world we live in, The same forces that produce supervolcanoes and mass extinctions also produce fertile soils, mineral deposits, hot springs, and the very atmosphere we breathe. Creation and destruction are two sides of the same geological coin, and the coin has been flipping for 4.5 billion years. Close your eyes now. Let your breathing slow. Feel the weight of your body, the warmth of the air, the quiet of the room. The earth is beneath you, steady and ancient. The stars are above, distant and patient. And you are here, in between, alive and aware and part of it all. The supervolcanoes are sleeping. The magma is rising, slowly, imperceptibly, somewhere deep below the surface. But it will be a long time, a very long time, before it reaches the surface again. And in the meantime, the earth is quiet, the ground is still, the night is peaceful. Sleep now. Let the deep time carry you. Let the ancient rhythms of the earth, the slow convection of the mantle, the gentle drift of the continents, the patient accumulation of sediment on the ocean floor, be your lullaby. They are slow rhythms, measured in millions of years, and they are deeply, deeply calming. The earth has been doing this for 4.5 billion years. It knows what it's doing. And tonight, it's holding you gently on its surface, turning slowly through the darkness, carrying you toward morning. You are safe. You are warm. You are home. The story of the earth continues. In the rumble of distant earthquakes, in the quiet hiss of geysers, in the slow growth of crystals deep underground, in the patient drift of continents across the surface of a molten world. It continues in the fossils buried in the rocks beneath your feet, the bones of creatures that lived and died millions of years before you were born. It continues in the chemistry of your body, in the carbon and oxygen and iron and calcium that were forged in stars and delivered to the earth by comets and meteorites and the slow rain of cosmic dust. You are made of the earth, and the earth is made in part of you. Sleep now, sleep well, and know that you are part of something ancient, something vast, something endlessly resilient. The supervolcanoes may sleep for millennia. The mass extinctions may be millions of years away, and in the meantime, life goes on, quiet and green and persistent, growing in every crack and crevice, filling every niche, reaching for the light. Good night. Dream softly. Dream of ancient seas and young mountains. Dream of forests growing over the ash of old eruptions. Dream of life, endlessly creative, endlessly resilient, finding a way. And so, under the quiet stars, on the surface of a restless planet, the story continues, slowly, patiently, beautifully. I hope you sleep well, dream deeply, and wake up tomorrow feeling refreshed, restored, and ready for a new day. Good night.